Hi, class. So welcome back. And we're still in chapter 14. This lecture, we're going to be working on chapter 14.2 that has to do with pH and pOH. So in the last segment, chapter 14.1, we learned about the definitions of acids and bases and how to write some equations and how to identify the different species in those equations. Well, this time we're going to do something different. We're going to calculate or try and learn how we measure the acidity of solutions that contain acids and bases. We could say the acidity or the basicity. So we're going to learn a few terms. Acidity, acidic, alkaline are terms that we're going to use to describe how acidic or basic solutions are. So let's get started. I'll share the video. We do have a worksheet at the end. This will be worksheet 15, and it'll be involving the concentration calculations for acids and bases. And so let me just share my screen. Here we go, the desktop, and I'm going to click on the PowerPoint. And here we go. So a couple of objectives. Know how acid concentration, acid strength, and acidity are related. And let me just switch to my camera. There we go. Okay. Number two, know how hydronium ion concentration, remember the hydronium ion, relates to hydroxide ion concentration. Lastly, be able to calculate pH and pOH from hydronium ion and hydroxide ion concentrations. Well, pH is a measure of maybe a shorthand way to describe the acidity, how acidic a solution is. And pOH is a complement of that. So you might not have, I'm sure you've heard of pH. That's a pretty common term, but you might not have heard pOH. Well, pOH is the complement of pOH. It's the hydroxide ion concentration. It's a way to describe the hydroxide ion concentration. So let's look at what's going on with water, first of all. So if you just have a cup of water, glass of water, a beaker of water, tap water, but it's pure water, nothing else in it, water can self-ionize. Now, it doesn't do this to a very great extent. We actually say water is neutral. It doesn't contain any ions. It's molecular. That's how we describe it chemically. It's a molecular substance. But to a certain extent, water can act as one water molecule can act as an acid. Say this is the acid. That means it's going to lose its hydrogen ion. The other water molecule can act as a base. So if this is the base, and the other one is the acid, that means a proton is going to leave the acid and go to the base, which maybe it went the other way, but that's okay. We're going to end up with a hydronium ion and a hydroxide ion. And so this doesn't happen to a very large extent because, like we all know, water does not contain ions. But in water, this determines the amount of hydronium ion and hydroxide ion is limited by this equilibrium. And so let me back up a little. We know water is not very ionic, so there aren't very many of these. There's not very much hydronium ion, not very much hydroxide ion. But this does happen. There's not enough when if we tried to, you may have done this experiment in a lab where you put electrodes in water to see if there was any conductivity. So if conductivity in an aqueous solution indicates there are ions present. Well, if you use pure water, there's no conductivity. You can't measure a current. If you add a little sodium chloride, that produces some ions, and you get conductivity, enough to light up a light bulb. But anyway, going back, this is called the self-ionization of water. It doesn't amount to much, but we can write an equilibrium. This is an equilibrium, so there should be a backwards arrow here. This isn't written quite correctly. We should have an arrow going both ways. This is an equilibrium. And that means we can write an equilibrium constant. That's called the ionization constant for water, or the ion product constant for water. And we know how to write those. It's a concentration of H3O plus times the concentration of hydroxide divided by the reactants. But the reactants in this case have a little L here because it's liquid water, right? What do we know about substances, liquids, and solids in equilibrium expressions? You don't include them. So our expression for the self-ionization of water looks like this. Kw, we call that Kw instead of K subscript C. It's specific for water, so we do a subscript W. So Kw is equal to H3O plus times OH minus. And that value at 25 degrees C is 1 times 10 to the minus 14th. This is a really important physical constant for water. So anything in water, especially acids and bases, has to obey this equilibrium. What we know about equilibrium is that if you increase one, you have to decrease the other to maintain the constant. Now, is that constant big? What does that constant favor? What do we know about equilibrium constants? We know that if it's really small, it means the reactant side is really large. So this particular equilibrium constant for water, 1 times 10 to the minus 14th, greatly favors the reactant side of this equation. So the reactant side is huge. There's only about 1 in 10 million hydronium molecules and hydroxide ion molecules. And how do we know that? Well, if we ionize the water, that means we're going to get 1x here, right? So it's whatever we start with, we do plus x here. We'll get plus x here. We do a kind of a very quick abbreviated ice table. This would be plus x when we ionize it. So if we put x here times x, I'm just going to take a shortcut, x. This becomes x squared. This is equal to 1 times 10 to the negative 14. And if we take the square root of both sides, let's take the square root. We'll go to the 1/2. Okay, we're going to go to the 1/2. That means that x equals 1, let me go on, 1 times 10 to the negative 7 moles per liter, molar. So that's what in pure water, hydroxide ion concentration is equal to the hydronium ion concentration. All right. So what else do we know about equilibria? We know that if you increase one species, the other one has to decrease. So if we increase the H3O plus by adding acid to the water, hydroxide ion has to go down to maintain this. We talked about that previously. If you add base, if you add sodium hydroxide and you increase the hydroxide ion, then the H3O plus has to go down to maintain the equilibrium constant at 1 times 10 to the minus. So if H3O plus is greater than 1 times 10 to the minus 7th, the solution is called acidic. I'll come back to that. I think I have a summary table for these terms. Hydroxide ion is greater than 1 times 10 to the minus 7th normal. It's basic. If they're both 1 times 10 to the minus 7th molar, so if the concentration of hydronium ion and hydroxide ion are both 1 times 10 to the minus 7th molar, that's said to be neutral. So this particular equation that I've solved here is for a neutral water solution. That's what we call neutrality. Neutral or neutrality? Neutral. Okay. So what else can we do with this equation? Let's see. That's a little hard to see. Maybe I need to erase some stuff. So if H3O plus equals 7.5 times 10 to the minus 5th molar, what is the hydroxide concentration? So H3O plus is 7.5 times 10 to the minus 5. Is that greater or less than 1 times 10 to the minus 7? So let me go back. Let me go write down 1. Let's see. 1 times 10 to the minus 7. Whoops. That 1 times 10 to the minus 7 is really important. So let me write that up here and keep that up here. 1 times 10 to the minus 7. Remember, that's the concentration of hydroxide and hydronium ion when it's neutral. So if H3O plus is 7.5 times 10 to the minus 5th, that's greater than that. That means this is an acidic solution. So let's think of that first. This is acidic. So what's the hydroxide ion concentration? Well, we have an equation here, right? So if we plug 7.5 times 10 to the minus 5th here, we can solve for hydroxide. So hydroxide is going to be 1 times 10 to the minus 14. So 1e, I'm going to do this in my calculator, 1e to the minus 14th divided by 7.5 e to the negative 5. When we do that, we get 1.33 times 10 to the negative 10. So the other way we can figure out whether these solutions are acidic, neutral, or basic is look at the hydroxide ion. If hydroxide is less than 1 times 10 to the minus 7, it's acidic. If hydroxide is greater than 1 times 10 to the minus 7, it's basic. So in this case, we have an acidic solution. Everything lines up. Everything has to line up. Okay, so the hydroxide concentration and the hydronium ion concentration have to both indicate that the solution is acidic, basic, or neutral. So one other term I wanted to add. Previously, we learned that in the self-ionization of water, water can be an acid or a base. And I'll put my labels back up here again. It can be an acid or a base. So a substance, a single substance can act as an acid or a base, is said to be amphoteric. Now, there are other definitions of acids and bases that we haven't talked about. So amphoteric is generic, very broad. It includes any substance that can act as an acid or a base, and that can be any kind of an acid or a base. We're talking about acids and bases that just transfer protons, like we're talking about now. Another name for that is amphiprotic, and I think that's what it calls it. It says in your book. I think it's called an amphiprotic substance. So it's amphiprotic or amphoteric are both the same kind of substance. So these are definitions we talked about. You might want to write those down. All right, next. So those numbers that we just looked at, let's go back up here. 1 times 10 to the minus 14th, 7.5 times 10 to the minus 5th. It's a little awkward, takes a little time to write those. So chemists have invented a scale called the pH scale, which takes these numbers, which are pretty small, and takes the log of them, which transforms them into numbers between, for acids and bases, roughly between 0 and 14. So these are whole numbers. So our pH scale typically runs between, well, I would say for the kinds of acid and base concentrations we use, -1 up to 15. But usually when you hear somebody talks about the pH scale, they're talking about 0 to 14. But when we talk about, when we actually calculate pHs, they can calculate between 0 and -1 to 15 typically. Maybe a little less than -1, maybe -1.5 are the strongest acids. So because the pH is a log scale, it's a negative log scale. You know, if you take the log of a number less than 1, it's going to be negative. And so remember, all of our numbers, all these are less than 1. Typically, they're less than 1. So when you take a log of a number negative one, less than 1 is negative. So that's why we take the negative value of it. Take negative log of the hydronium ion concentration, because we want the number, the pH scale, to be a positive number, not a negative number. Now at high acid concentration, say 1 molar, 2 molar, well, above 1 molar, 2 molar to 6 molar, acids can get up to about 12 molar. 12 molar in hydronium ion, you're going to get a negative pH. So if you take the log of 12 and then you take the negative of it, what you get is -1. You can also calculate a pOH, which is minus the log of hydroxide ion. So that's where the pOH scale comes from. And they're opposites. So if the pH scale goes up from 0 to 14, and this is pH. The pOH does the opposite. The pOH goes from 0, from 14 to 0. And what that means, and this is a result of the ionization product constant. You know that we wrote the equilibrium constant expression for water, where H plus, or H3O plus times hydroxide ion equals 1 times 10 to the minus 14. If you convert the H3O plus to pH and the pOH and the hydroxide ion concentration to pOH, and you'll find out that pH plus pOH is equal to 14. So this is a direct result of the equilibrium constant. So pH plus pOH equals 14. That's why the scales run opposite. So if pH is 14, pOH is 0. If pH is at neutrality, they're both 7. pOH, or if pH is 0, pOH is going to be 14. This is kind of nice because if you know the pH, you can just take 14 minus the pH and get the pOH. So these are some calculations I'm going to ask you to do. So this is really handy to know. So I have a little video here I want to show you about pHs. These are common solutions. We have bleach, baking powder, sanitizer, sugar solution, water, Sprite, vinegar, and lemon juice. They go from basic to acidic, and you see they have different colors, but this is kind of cool. This might be something that you would like to do at home. So here's the video, and I kind of got smart. I loaded this. Hopefully it'll run without an advertisement. Let's see. It did. Wow, wasn't that cool? So let me get back to my PowerPoint. There it is. So you can do this at home. You can show your family, your brothers, your sisters, your friends what you're learning in chemistry. So this is, it turns out that purple cabbage juice is a natural pH indicator. It's like a universal indicator. So look at all the colors that cabbage juice changes to at the various pHs. So you're going to learn about pH indicators in lab. So let's go on. So let's look at this pH scale. So this is a scale that I kind of sketched out previously. On the left is the hydrogen ion scale, the hydronium ion scale, and on the right is the hydroxide ion scale. And right in the middle is neutrality. So if the concentrations of both are 10 to the minus 7, the pH is 7. So I'd say the pH here is equal to 7. And the pOH is also equal to 7. So I can write the pOH over here. pOH is also equal to 7. Okay. Now, what if we tell them, what if we add, what are we going to add here? We added some acid to it. So we added HCl to that. Well, that meant that the concentration of H3O plus went way up. So 10 to the minus 2. So the pH at 10 to the minus 2 is 2. And how do I know that? Because the log of 10 is 1. And minus 2 is plus 2. I don't know. We just know that. So since it's a LOG scale, it's a log base 10, that if you have just power of 10, the pH is equal to the minus the exponent. So the hydroxide ion then is 10 to the minus 12, so the pOH is 12. Plus 2 is 14. Remember that one? pH plus pOH equals 14. What happens if we add sodium hydroxide to the water? Well, the oxide concentration goes way up. So the hydroxide ion concentration now is 10 to the minus 2. So the pOH is equal to 2. And the pH now is 12. And this solution is basic now. So there's several ways to describe a basic solution. We can say that the pH is greater than 7, or the pOH is less than 7. Previously, we could describe an acidic solution, a pH is less than 7, or pOH is greater than 7. Another way to describe an acidic solution is that the H3O plus concentration is greater than 1 times 10 to the minus 7th. So there's all these different ways. Just think about it. There's lots of different ways to describe a solution as being acidic or basic in terms of pH, pOH, hydronium ion concentration, or hydroxide ion concentration. Now, when we're doing these calculations, the worksheet we're going to work on has to do with calculating. This is a pretty handy little tool to use. And in Canvas, when you get to the page, the module page for chapter 14 that has the worksheets on it, I have a link to this page. You can download this. If you think this is helpful, I download it and keep it handy while you do these calculations and while you do the homework, and also when you do the test. This is a pretty handy little page. It's out there for you on Canvas under the worksheets on page for chapter 14. So you can see how pH and H plus are connected. pH equals minus the log of H plus. H plus is 10 to the minus pH. If you want to convert between hydrogen ion and hydroxide ion, hydroxide is 1 times 10 to the minus 14 divided by hydrogen ion. Hydrogen ion is 1 times 10 to the minus 14 divided by hydroxide ion concentration. Okay, so I'm not going to go over all these, but you can read those when you get a chance and see how you convert. We already said that pH and pOH, pH plus pOH equals 14, so you can convert between those two values also quite easily. So here's a few things. A summary chart says in acidic solution, H3O plus is greater than H and then hydroxide. So hydronium ion is greater than hydroxide. And the pH is between 0 and 6. In a basic solution, hydronium ion concentration is less than hydroxide. pH would be between 8 and 14. In a neutral solution, the hydronium ion concentration is equal to the hydroxide ion concentration. The pH is 7. And the H3O plus is 1 times 10 to the minus 7th, and hydroxide is 1 times 10 to the minus 7. So that's the end of that. I'm going to stop sharing this screen now. And here's the sheet I was just showing you on the PowerPoint. And like I said, that's really a handy, I find it handy. It's a graphic visual connection between these different units of concentration or measurements of pH, of acidity and basicity that we talked about. So let's do the worksheet. So I'll do what we did last time is I'll work some problems and leave some problems for you to work. So this is worksheet 15. Whoops, what happened to it? There we go. Okay. Worksheet 15 for section 4.2. Come on. There we go. Okay, determine the pH of the following equilibrium concentrations of hydronium ion. Use the correct number of significant figures in your answers. Okay, so the sig figs have to do with how many sig figs are in the coefficient of the scientific notation number, okay? So here we have 3 sig figs. So that means when we take the logarithm of that, we want to have 3 decimal places. So the number of sig figs is going to equal the number of decimals in our log. in our pH value. So what we need to look at is, we know that H3O, remember this, H3O plus, I didn't do that right. Let me say minus the log, there we go, minus the log of H3O plus is equal to pH. So that's the calculation we have to do here. So that's what we're going to do for all these. So I'll do the first two. And we'll just calculate the pH. That's pretty simple if you can do this on your calculator. I think you should try it on your calculator, see if you get the same thing I do. 1.8 e to the negative 5. I'm going to take the log of that, and then I'm going to change the sign, and I get 4.7 here. So pH is equal to 4. I want to do, there's 3 sig figs, so it'll be 3 decimal places, 7, 4, 5. So the pH is 4.745. Let's look at the next one. So, and the other thing I want you to figure out is this acidic or basic? Well, the pH is less than 7, so it's acidic. It doesn't say that in the directions, but I think I want you to determine if it's an acid. Is it acidic or basic? Okay, think of that also while you're doing these. Okay, what's the pH of the next one? We're just going to take the log of 7.98 times 10 to the minus 9. And take the log of that, change the sign. That's how I do it on my calculator. So the pH is 8. There's 3 sig figs, so the 3 decimal places, 0.98. Okay, and I'll let you guys do numbers 3 and 4. Is this acidic or basic? Well, the pH is greater than 7. That means it's basic. But the hydrogen ion concentration is less than 1 times 10 to the minus 7. So that also means it's basic. So you can look at this to determine the hydrogen ion concentration, to determine if it's acidic or basic in relation to 1 times 10 to the minus 7. That tells you, or you can convert it to the pH and figure it out. Okay, so you do the next two. 3 and 4 is for you to do. So let's determine the pH for the following concentration of hydroxide. So there's a couple ways we can do that. We can, if you remember, let's see, find the pH for the following concentration of hydroxide. Oh, determine the pOH. Ah, okay. So that's the same thing, determine the pOH. So we want to do, let's see, pOH is going to equal minus the log of hydroxide ion concentration. And so I'll do number 1, and you do the other ones. Also decide if it's acidic or basic. Let's look at this. 4.63 times 10 to the minus 3. Is that greater or less than 1 times 10 to the minus 7? Well, it's greater than that. So hydroxide is greater. That means it's basic. So that means our pOH should be less than 7. So let's see if it is. 4.63 e to the negative 3. And I'll take the logarithm of that and change the sign. I get 2. I have pOH, oops, pOH equals, and I'm going to put 3 decimal places again, 334. What if I want to know what the pH was? Well, the easy way is to subtract it from 14. 14 minus 2.334 comes out to be 11.666. So these are all consistent with the solution being basic. So remember, to get the pH, I got that because pH is equal to 14 minus pOH. Okay. So I took care of that one. I want you guys to do numbers 2 and 3. And if you have any questions, let me know. I think these are pretty straightforward calculations. Also label these solutions at these different pH and pOH concentrations as acidic or basic. Right, here's another one. Let's see, we have 2 more. I'll do one and you can do the other one. Determine the pH of the following solutions and label each solution as either acidic or basic. This is sort of what we did before. So I'm going to take a different approach. Another way to find out. So this is calculating the pH. So the pH is minus the log of H3O plus. You can use H plus instead of H3O plus, that's okay. But we know that H3O plus, this is just a different tact, a different way, is equal to 1 times 10 to the minus 14 divided by hydroxide ion. You can find these on that sheet I showed you. I guess it's a kind of a roadmap for doing these calculations. Concept map, that's what we call it, concept map for doing these calculations. So I'm going to use this approach. I'm going to take 1e to the negative 14. I'm going to divide it by the hydroxide ion concentration, which is 3.55 e to the negative 10. When I do that, I get hydrogen ion concentration is 2.8 3 sig figs, 2 times 10 to the negative 5, 10 to the negative 5. And so if I take the log of that, and then I change it, I get a pH of 4.55. So that's my answer. So that's one approach. This is step 1. This is step 2. Is minus the log of 2.82 times 10 to the negative 5. Let's see, 3 sig figs. I need to put one more. There's a 0 after it on the calculator. So does that make sense? Well, that's an acidic pH. The hydroxide ion concentration is less than 1 times 10 to the minus 7, so that matches, that's acidic. Hydronium ion concentration is less, is greater than 1 times 10 to the minus 7, that makes it acidic. So all these are consistent with an acidic solution. All right, so you do number 2, and there's another way you can do it. You can figure the pOH, and they do 14 minus the pOH to get the pH. You know, whatever works best. There's always 2 ways to solve these problems. So you guys do number 2. Let's see what you come up with. The last one, let's see, determine the hydronium ion concentration from the following data and label the solution as either acidic or basic. Well, the pH in the number 1 is 4.165. So I would say that's acidic because it's less than 7. The pH is less than 7. That makes it acidic. And to find the hydronium ion concentration, if we look on our concept map for doing these calculations that I showed you, it's 10 to the minus pH gives you your hydronium ion concentration. So we'll go 10 to the negative 4.165. So I happen to have a key here on my calculator. Show you right there. It's right there, the 10 to the x. So hopefully you have that. It's right above the LOG key. So this is the log key that I've been using. So I'm going to put in, I'm going to do shift 10. Okay, I didn't want to do that. I put in my number first. So my number is negative 4.65. So I'll put 4.65 and I'll change the sign. Wrong. 4.165, change the sign. And then I'll do the 10 to the x. And I get H3O plus is equal to 6.84. Let's look at this. The pH is 4.6165. There's 3 decimal places. So I have 3 sig figs in my coefficient of my scientific number. Sorry. My answer was 6.84 times 10 to the negative 5. Okay. And we already figured this was acidic, and that matches. Okay, so you can do this next one. The next one has an extra step because we're starting with pOH instead of pH, but I think you can figure that out. So that's the end of section 14.2, talking about the terms used to describe acidic solutions and basic solutions, and how to calculate pH, pOH, in the hydronium ion and hydroxide ion concentrations. So that's it for now. Take care, and I'll see you later.